This is our last section for chapter 14. It's chapter 14.6, and we're also going to throw in chapter 14.7. It is a little bit shorter, so we're going to do both of them together. Chapter 14.6 deals with what are called reaction mechanisms. We're going to talk about what a reaction mechanism is. We're going to talk about what are called elementary steps. We're going to talk about the rate determining step and these intermediate species today. Then we're going to talk about how you can get a rate law from a reaction mechanism. So a lot of times in a chemical reaction, we can see the reactants, we can see the products, but we don't necessarily know how the reaction occurs. And what that means is that basically a lot of times in a chemical reaction, you've got your reactants, you've got your products, but there's many, many small steps that occur during the reaction before we actually get to the final product. And so what you can do is you can write what's called a reaction mechanism for that reaction that shows each step of the reaction as it proceeds. So they can be pretty simple, one or two steps, or they can be, sometimes 4 or 5 steps, pretty complicated. So we're going to begin with simple steps of how a reaction begins. We know that for a reaction to occur, obviously the molecules have to collide with each other. When a single collision occurs with enough energy, it's got a correct orientation. What we call that is an elementary step, and that's when, again, one thing hits another thing and that reaction happens. The number of molecules that participate as reactants in an elementary step defines what's called the molecularity of the step. If just one molecule is changed by the reaction, we call it unimolecular. If two reactant molecules are changed, it'd be bimolecular. And if you actually happen to have three things hit and change at the same time, which is very unlikely, it would be called termolecular. So if we look at this reaction here, we've got H3CNC becoming H3CCN. That would be a unimolecular reaction simply because one molecule is colliding with itself. The other molecule, no other molecules are changing, and then you get your product. In this case, notice that we've got two things that would be changing. You've got the NO changing, and you've got the O3 changing. That would be a bimolecular process, where the NO is colliding with the O3 to produce the products. In this case, you've got NO2 reacting with NO2 to become NO3 and NO. That would also be bimolecular. Although it is one molecule, notice that you're ending up with two different products, so both of these molecules are changing. Whereas up here, if these are colliding with each other, which they actually weren't, these are just basically the C and the N are changing places. The C's going here, the N's going there. Then you don't have this. This is still the unimolecular here. And then, like I said, the chance of three molecules colliding at the exact same instant is very remote, and I've never seen that happen where that would occur. So in a lot of cases, there's more than just one elementary step in a reaction. A lot of reactions have what we call multi-step mechanisms, which is basically 2 or 3 or 4, or maybe 5 or 6 steps of elementary steps that produce an overall reaction. For example, ozone, the ozone layer protects us from the sun's ultraviolet rays. When it converts to molecular oxygen, it's not done in just one step. What we see here is this is the equation that we would write down. This is the overall equation. But what actually happens is one of the sun's rays hits one of these ozone molecules and it breaks apart into oxygen molecule and an oxygen atom. And then what happens is that oxygen atom then reacts with this another ozone molecule, and then both of them turn into oxygen atoms. Notice that overall, though, basically anything that's the same on opposite sides of the equation we cancel out. So notice that we produce an oxygen atom here, we use that oxygen atom again here, and so overall, in the overall reaction, notice that we do not see any oxygen atoms at all. Okay, we'll talk about what those are here in just a minute. But for right now, notice that in the overall reaction, we have our two ozones, and then we've got our 3 oxygens. So when we write out the balanced equation, it looks like a one-step process, but when really it's a 2-step process for it to occur. And a lot of reactions do that. So that oxygen atom I was just talking about right here, since that oxygen is formed in one reaction and then it's used up in a subsequent step, and it doesn't have to be the next step. If you know, a lot of times you'll have 4 or 5 steps in a reaction. It can be produced in the first reaction, then not used again until the third or the fourth. When that happens, that oxygen atom is called an intermediate. So an intermediate is something that is formed in one reaction, so it's formed in one step, and then it's used in one of the following steps. Usually it's the first one. So here we've got a reaction. MoCO6 breaks a carbon dioxide off, and you get MoCO5. So notice that we're making MoCO5, and then we're using it again. So in the overall reaction, that would not be there. So your total reaction would be this plus this is going to make this plus all of that mess there. So overall, that MoCO5, that is your intermediate. Now, if we know that a reaction is an elementary step, and then the only way that we know that is if it's in a reaction mechanism. For example, this is a reaction mechanism right here that's showing the elementary steps. Okay, this one right here, this is a reaction mechanism. This is step 1. This is step 2. Okay, this thing down here is the overall reaction. Okay. So if we know that a step is an elementary step, which again we have to know that from a reaction mechanism, then we also know its rate law. The rate law of an elementary step is based directly on its molecularity. And what that means is, up until now, when we had rate laws, we would say the rate equals K times the concentration of A raised to some power times B raised to some power, maybe a C, maybe a D in there. But it was raised to some unknown power. What they're saying is, if it is an elementary step, then you can use the balanced equation to produce the rate law. So if it's unimolecular, it's going to be first order. Okay? If it's bimolecular, we know it's going to be second order and so forth. So basically what I'm saying is you can use the coefficients from the balanced equation to write the rate law if you know that it's a single elementary step. Okay? But again, we can't tell by looking at a balanced equation whether the reaction involves one or more elementary steps. Unless they have the reaction mechanisms written out, then we can say, yes, this is an elementary step. So we could come back to this equation right here, and you could say, okay, what's the rate law for this reaction right here? And it would be the rate would equal K times the concentration of O3 raised to the first power. Okay, what would be the rate law for the second one? Let's just say there's a 2 there, just to make it a little bit different. Because we know that's in a reaction mechanism, we can say the rate would equal K times the concentration of O3 squared times the concentration of O. So when you have an elementary step, you can use the balanced equation, but in general you cannot. For the most part, you cannot use the balanced equation only when you know it's an elementary step. So here's a reaction between nitrogen dioxide and carbon monoxide. You've got NO2 reacting with CO to make nitrogen monoxide and carbon dioxide. So basically an oxygen is trading places. That appears to proceed in just one step. However, it doesn't. It occurs in 2 steps. The NO2 reacts with itself to make NO3 and NO. Then the NO3 that's produced reacts with this other carbon monoxide that's here, and you get the NO2. So overall, notice that we're producing NO3 and we're using the NO3, so we know that that's our intermediate. And so that is, we can use that information to write the rate law. So we could say, in this case, the rate would equal K times the concentration of NO2 squared. Okay, because there's two NO2s there. Okay, so here if it's unimolecular, blah, blah, blah. If it's bimolecular, you have two A's, just like the one we just saw, then it's A squared. Obviously, it's very similar, very easy to determine there. Now, if we know that a reaction only has one elementary step, we can use the coefficients of each reactant in the balanced equation to determine the rate law. We just did that. So, for example, in the reaction 2NO plus Br2, and here's the important part, which only has a single elementary step, and they would have to tell you that. So they would either have to say that, or it would have to show, okay, here's step 1, here's step 2, here's step 3, and so forth. And then those would be your elementary steps, and you could write the rate laws of those. But because they tell us that it's a single elementary step, then we know that there's two NOs, so it's NO squared, and there's one Br2, so it's just Br2. Now, most reactions are going to involve more than one elementary step, each with its own rate constant and its own activation energy. But a lot of times what happens is you might have like a 4-step process, 1, 2, 3, 4. And just like a chain is only as strong as we know, its weakest link. Well, let's say the first reaction is really, really fast. The second one is pretty slow, and then the other ones, no, not slow, let's say fast and fast. How fast is this reaction going to go? Well, it all depends on your slowest step. So often one step is much slower than the others. The slowest step limits the overall reaction rate and is called the rate determining step. So the rate determining step is always the slow step. Because this goes by fast, fast, and fast, but it's this one right here that's really going to determine overall how fast that reaction is going to go. So the rate determining step really governs the rate law for the whole overall reaction. So we don't even necessarily care about the fast steps. The only one we care about is the slow step. So we just talked about this reaction, NO2 reacting with carbon monoxide, and those were our two steps. It appeared to have appeared in just one elementary step, but we know that the rate law is actually the rate equals K times NO2 squared, meaning that the concentration of carbon monoxide plays virtually no factor in the rate at all. So tell me right now, is it this, slow, fast, or is this the fast step and this one the slow step? So the rate law is rate equals K times NO2 squared. That's the key. That means that that step that involves those has to be the slow step. So that's telling us that the slow step has to be this first one right here. So this one's slow, this one's fast. Okay, so since carbon monoxide has no impact on the rate, it's involved in the fast step, whereas the reaction with NO2 is a slow step. If CO were involved, the rate law would involve obviously the carbon monoxide and the NO2. Okay, we've got a problem though. Some rate determining steps in a mechanism involve an intermediate. But intermediates, as we know, do not appear in the overall equation. Just like that one we saw with ozone a while ago, the one with ozone that had the oxygen atom in it, in the overall equation, we didn't see it. We never see oxygen atoms in there. Here it is right here. So, for example, if this is the slow step right here, let's say step 2 is the slow step, then we would write the rate as rate equals K times O3 times O. But again, you can't do that because look at our overall equation. There's no oxygen in the overall equation. So that's going to be a problem is when we have intermediates that are in our rate law that honestly can't be there because they're not part of our overall equation. So what do you do with the intermediate? In a reaction that contains a multi-step mechanism, whenever a fast step precedes, so comes before, Whenever a fast step comes before a slow one, we can solve for the concentration of an intermediate by assuming that an equilibrium is established in the fast step. And I'll show you what that means here. So let's say we've got this reaction here. We've got the net reaction of 2NO plus Br2 making 2NOBr. The rate is found to be blah, 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 blah. Use the following mechanism to produce a rate law that's consistent with this rate law. Now, we've got our fast step, we've got our slow step. The slow step is the rate determining step. So, if we take this second reaction, the rate law should be rate equals K times the concentration of N2O2 times the concentration of Br2. Again, the problem is in our overall reaction, I don't see N2O2 at all. And the reason is because it's an intermediate. What that means is that notice right here we've got an equilibrium arrow. That equilibrium arrow means it is just that you're at equilibrium. That means that the forward reaction is going just as fast as the backwards reaction. So if we take, basically we're going to turn this into two reactions. We're going to write a forward reaction and we're going to write a reverse reaction. So we're going to write the forward reaction as the rate is equal to K times NO squared. Okay, that's for the forward reaction. For the reverse reaction, which is basically N2O2 going back into NO and NO, it would be the rate equals K times N2O2. Now, what we just said is that we're at equilibrium, which means this rate, the forward reaction, this rate, the reverse reaction, are equal to each other. If they are equal to each other, then we can just set these two things equal to each other as well. So we can say that K times the concentration of NO squared equals K times the concentration of N2O2. Notice the K's, they're going to cancel each other out. So what we've got here is that the concentration of NO squared is equal to the concentration of N2O2. So what we do is in our rate law that we just created that has our reaction mechanism in it, or it has our intermediate in it, is we replace the intermediate with whatever it is equal to. So we take the NO, we put it right down here in place of the N2O2. So our rate law becomes rate equals K times NO squared times Br2. And then notice that our rate law is consistent with the one that they wanted us to form. Okay, so this is kind of just me explaining that whole thing there that I just explained. So we're going to substitute that into our equation. Our K's cancel each other out, blah, 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 blah. So let's, I want to kind of I'd like to do another example with this. Let me see if I can come up with one here quick. Look at how fast I came up with that. So A plus B is in equilibrium with C plus D, and that's the fast step. And then in our second reaction, we've got C plus E making F and G, and that's our slow step. So overall, if we were to ask to find what's the overall reaction, it looks like our only intermediate is C. So it would be A plus B plus E would make D plus F plus G. Notice that anything that's on the reactant side that doesn't cancel out is there. Anything on the product side that doesn't cancel out is there. Okay? Now, if we were asked to find the rate law for this reaction, this is the important part here. The rate law is based on the slow step. This is our slow step right here. So I would say the rate is equal to K times the concentration of C times the concentration of E. But again, C is an intermediate. So C is, we can't have it in our overall rate law. So what we're going to do is we have to come back up here and we're going to make our two equal to each other again. So rate equals K times A times B for the forward reaction. Rate equals K times C times D for the reverse reaction. They're at equilibrium, which means their rates are equal to each other, which means the K's are going to cancel out. So it's going to be A times B equals C times D. Here's our rate law. Remember, we got to replace C with something else that's in the overall equation. So I've got to get C by itself. How do I get rid of D? Well, obviously it's multiplied, so I just divide by D. So it's going to look kind of funny, but again, that's the sort of things they ask you about on the AP exam. So this rate is going to be rate equals K. Now instead of C, I'm going to write what C was equal to. C is equal to A times B times, here's our E over, and remember we put the D on the bottom, the concentration of D. And that, as funny as it looks, is the correct rate law for that reaction. That D we had to move over to that side to get C by itself. Okay, so that's it for that section. Here's your homework. A few questions there. We're going to finish up with catalysts here, and then we're going to be done with chapter 14. So chapter 14, part 7 is about catalysis, which is just a catalyst. Like I said, this is pretty quick. A lot of reactions can be increased by the use of a catalyst. A catalyst is something that changes the speed of a chemical reaction without undergoing a permanent chemical change itself in the process. So there's two different ways a catalyst can work. It can either A, basically provide a place for the reaction to happen. In a catalytic converter, which is part of the muffler in your car, there's plates that are platinum and palladium, and what they do is they work because bonds are stretched and more easily broken when they come in contact with the platinum and the palladium. So the important part is right here. What the catalyst does is, one thing it does is it lowers the overall activation energy. So if you've got a reaction that looks like this, and it's catalyzed, what it will do is it'll start in the same spot, it'll end in the same spot, but basically this part right here will be lower. So you've got a lower, here it went up that far, here it only had to go up a little bit. So the activation energy can be lowered. Okay, the second thing a catalyst can do is it's usually, what it'll do is it'll be a reactant and then it will be a product. So it's a reactant in one step and a product in a following step. But just like an intermediate, it does not appear in the overall reaction. So we want to make sure we can clarify the difference between an intermediate and a catalyst. For example, here in this reaction, the HCOOH2 plus is formed and then it's used again. That is an intermediate. Okay, it forms HCO plus and the HCO plus is used again. That is an intermediate. A catalyst is something that you start with and then you end up producing again. So in this case, we're starting with hydrogen, H plus. It's being formed again. That is a catalyst right there. So notice the difference. An intermediate is formed and then used. A catalyst you start with and then you end up producing again. So in the overall reaction, look at all this stuff that cancels out. The overall reaction, you would just have HCOOH. This is gone, this is gone, this is gone. From the products, this is gone, that's gone, becoming H2O plus CO. So it goes from a very, very complicated three-step 1, 2, 3 reaction mechanism to a pretty simple overall equation. Okay, and then one of the things we talk about with the catalyst, if a catalyst is present in the same phase as all the other molecules, we call it a homogeneous catalyst. If it exists in different phases, then we call it a heterogeneous catalyst. And then in your bodies, you find that enzymes provide a substrate. They basically lower the activation energy in your bodies for a lot of the chemical processes that happen. So the only one that deals with that is question 6C in your packet. So take a look at that along with your other problems. We'll talk about it tomorrow.